So we're going to take a look at Chapter 5, which is based on numeration systems. And so in this first section, we're going to represent numbers and complete calculations using the Egyptian system, the Roman system, and the Chinese system. And what it's important to note here is that what we're doing is we're converting units. So the skill really isn't about the arithmetic, but it's about converting the units over to something meaningful. So a number really just stands for a quantitative measurement. So it's the number of objects that are being counted. And a numeral is the symbol that represents a number. So theoretically, in the English language, we know that 2 means 2 objects because the symbol 2 has been giving the meaning of 2 of an item. The number 10, for example, means we have 10 objects. So in every language, there is a word for 10 or 2 that relates back to the number of objects. And so in the Egyptian system, it was formed based on powers of 10, very much like our system, but the symbols are going to look different. And the symbols are going to be what was relevant to them in their time. And so as I'm writing the numbers out, what's unique about looking at our number system and any other really ancient number system is that we have a place value where a 3 right here is a place value of 300, but I just write one symbol. In other ancient societies, they write 3 symbols for 100 to mean the same thing that our number 3 means. And the same is applied for the tens place. So even though I know that the number 2 indicates I have 2 tens, I represent that with one symbol. They don't do that in Egyptian or Chinese or Arabic. They write the symbol for 10 2 times and then on to the 1. So that's something that's slightly unique about our number system. So the order of the symbols is not important. So you can get some really crazy stuff going on here where I could put them all out of order and still have to realize this is 100, 200, and 300. This is 10 and 10, so that's 20, and then 1, 2, 3, 4, 5. So when order is not important, it can look really funky, but it's natural to us to write them in order. So if I want to convert this number in the Egyptian system to the Hindu Arabic system, that's our system. I have 3 values of 1,000, so that's 3,000. 4 symbols for 100, so that's 400. 2 10 symbols and 5 ones, which would be 3,425. So this is about recognizing symbols and not arithmetic. In order to add or subtract these numbers, the nice thing, I guess, about this system is that you're changing the symbols. You're just adding all the symbols. So if this line has 2 symbols for ones, and I add 3 more symbols for ones, then I'm going to have a total of 5 symbols. So you're really just combining the number of symbols, and then you have to regroup because I have 10 heel bones, which represents 100. So again, it's a little bit of an interesting situation because you're combining symbols and not place value. And then when you're subtracting, it's going to be the same idea. You're subtracting the symbols equal from one another. But notice I don't have enough tens in the top row to subtract. So instead, I'm going to convert that symbol for 100 into 10 additional tens, strike out what I've got in common all the way up to here, and then I have what I'm left with. The Egyptians also had a system for multiplication. And in this system, any positive integer could be written as the sum of powers of 2. So if you're looking at that first one, you're like, 1 is not a power of 2. It is 2 to the 0. So it technically is a power of 2. And there is basically a system that was in place to do multiplication because that is a basic math that is currently needed. So Egyptians also had a unique system of doubling things. And so if a craftsman is restoring a rectangular wall from the temple of Queen, not sure how to pronounce it, we're going to go with it. And if the wall was 13 feet by 21 feet, so 13 feet wide, 21 feet tall, use the method of doubling to determine how many square foot must be covered. Well, what does doubling look like? Well, 13 feet would be 2 to the 0 plus 2 to the 2 plus 2 to the 3. That equals 13. So to find that area, we would calculate 13 times 21 as taking that breakdown of powers of 2 for 13 and multiplying that by 21. And so notice I distributed the 21. So I have 21 times 1, 21 times 4, 21 times 8. And so that's what they mean. They don't literally mean doubling. It means write one of the numbers in that base 2 system and then distribute your multiplication. And so once I do that, I get 273. And so they would kind of work with this and just keep doubling things. So if I have 121, that's 21. 2 21s would be 42. 4 21s is 84, which is what we essentially did. And so then they would just keep doubling to find out what these values were. So doubling doesn't refer to doubling the quantity per se, but it's using that powers of 2 system to arrive there. And the Roman numeral system, this can be a little bit more familiar to most of us. These are the symbols that are used in the Roman number system. And so if we want to take Roman numerals and convert them over to our system, we're just going to write down what they stand for. So D stands for 500, C stands for 100, L stands for 50, X stands for 10, and so on, so we can convert the numbers. That's kind of an easier conversion for us. And then, of course, there's the convention that if a smaller number is written in front of a larger number, that is considered to be subtraction. So IV is actually 5 minus 1. IX is really 9. So you have to make sure you're aware of that convention. There are 2 restrictions to this. We can only subtract certain numerals. So for instance, we couldn't say VL to represent 45. We only use it with the 1s, the 10s, and then the larger figures. We can only subtract numerals from the next to higher, which is where that hierarchy comes from, of using the I, the X, the C, and the M. So if I want to work on translating between these number systems, let's look at what we would do. We would take the symbols. We would write out what the symbols represent. We know that C comes after, C is a lower value than M, so we know to do subtraction. We know that X is lower than L, so we do subtraction. And then we get our expanded form number. If I wanted to write 492, I would need 4 100s, 90 10s, and 2 1s. And so I would actually get there from doing this math. I would have 500 minus 100, 100 minus 10, and then the 2 1s hanging out. In the Roman system, some things you may be less familiar with is that a bar above a symbol means to multiply that value by 1,000. And a bracketing symbol with 2 vertical bars multiplies by 100. That's probably a very less known part of Roman numerals. The Chinese system also uses multiples of 10. So this is very similar to our system. It is a multiplicative system where numerals are formed by writing products of integers from 1 to 9, which is different than our system. So if I'm looking at this notation, I see the 2 symbols written next to each other, and what it's not telling me is I'm actually multiplying those 2 symbols. That's how we're getting there, is the multiplication of the symbols. So if I wanted to write 3,542, I'm going to take the value for 3, multiply it by the symbol for 1,000. Same thing, take the symbol for 5, multiply it by the symbol for 100, and so on. And so that's how I'm going to generate my system there. So this is kind kind of an in-between step to the Egyptian system and our system, where we just say straight off the symbol 3 is all we need.